FLOP is an acronym for floating point operation.
How many numbers can they crunch in a given period of time?
It's a unit of measure of performance.
And because it's a fairly easy way and a fairly unambiguous way of measuring computer speed, we tend to use those flops quite a lot to compare computers, sort of as marketing. So it's a little like, miles per gallon or how quickly you can accelerate cars.
And the nominal speed will be some number of flops. That's when you get into the other part of the acronym. So mega, for example, is millions. And you have giga, which is billions, tera, trillions, peta, which is quadrillion.
This thing can scale up to 100 petaflops.
And then exa would be quintillion. You're going up by a factor of 1,000 each time.
Unfortunately, just like in cars, that means people might emphasize flops.
First machines designed by Seymour Cray in the 70s were in the, I think it was around 150 or 160 megaflops.
It doesn't mean that a computer that has more flops is a better computer. And that's where flops, I think, are in some ways a drawback, because what we'd really like to know, what the scientists would like to know anyway, is how quickly can I answer my problem.
While we talk about the peak performance of the machine, what we are most concerned about is the science that's delivered on it. How fast does your weather model run?
We call this time to solution. The time to solution and the flops are related, but they're not the same thing.
There's a lot of R&D that's required, a number of interrelated technologies that have to be in place in order to build a machine that can be efficiently used.
One of the characteristics that is creating sort of an evolutionary step in the way people are doing science is that as they've gotten faster, these computer systems have also changed their composition somewhat from the way they have been composed in the past. Particularly what we're seeing is a growth of what we call multi-core, many-core systems. This is where you have a whole lot of computational processors that are working together.
One can argue that you could string up millions of small processors and in theory reach that computational performance, but you really couldn't run an application on it.
The Supercomputing Conference here is replete with people, science, software, centers, vendors that are telling you how to deal with this multi-core, many-core, heterogeneous computational environment that we live in. It's proving to be not quite revolutionary, but very much a force for the technology requiring reconsideration of at least the computational science approaches, and in many cases the actual science that underlies the technology.
So we're in a very interesting point in our industry right now, because we're looking at the next milestone, which is an exaflop, as it's called. And an exaflop is essentially a quintillion operations a second. So that means you have a computer that can do that many mathematical operations, x plus y, per second. There's been a lot of studies done as to, well, what science could you do if you had a computer of this size? With one of these exaflop systems, they do imagine that they could run a fully coupled Earth system model at, let's say, a kilometer global resolution, but also in a reasonable amount of time.
The way computational power is growing is there is a necessity to sort of reconsider how you did your software in the first place. So it's not quite a renaissance, it's more like an evolutionary step, I would say, but essentially the software and the hardware are advancing in step, and the goal overall, of course, stays the same, which is to do better modeling, to better reflect the realities that we're trying to understand.